Hello everyone, my name is Andrew Kim and welcome to my sixth video of AP Physics 1 review session. So this video will go through the Unit 6, which is simple harmonic motion. So let's get started. So this is the note for Unit 6, which is simple harmonic motion. Now, I have one interesting experience to share regarding simple harmonic motion. When I was in grade 5, I went to a physics camp. And in the physics camp, we started learning about simple harmonic motion. And literally what the professor told us is that we're going to start our session with simple harmonic motion because it is simple. Well, I want to tell you guys the same thing. Don't worry, simple harmonic motion is simple. You'll get it. You'll be able to learn it very easily. So let's get actually started. So first of all, what is the definition of a simple harmonic motion? Well, I would like to explain simple harmonic motion as a motion where restoring force is proportionate and opposite of displacement. Now, this definition is very lengthy. It's hard to understand. I'll explain it in an easier way. Simple harmonic motion is like your younger sibling. If, for example, I have a younger brother, when he's in my room, I always tell him to get out. If I tell him to come into my room, he will never come in. Always, it moves in the opposite direction as what you want it to move. So for example, the classic example of simple harmonic motion is when on a wall, you have a spring attached, and at the end of the other end of the spring, you have a box. Now, if you pull the box towards you, then there will be a restoring force towards the opposite direction that you're pulling. If this time you're not pulling the box, but if you're pushing the box towards inward, towards the wall, then again, there's a restoring force towards the opposite direction, which is towards getting farther away from the wall. So simple harmonic motion is a motion where the force is present always towards the opposite direction of where you're moving toward. That is why it oscillates. That is why it doesn't move towards only one direction infinitely, but it moves towards one direction, stops, and moves toward the other direction, stops, and continues that cycle. Why? Because if you start moving towards one direction, then there will be a restoring force towards the other direction, so you would change your direction of movement. However, once you change your direction of movement, then again, there will be a restoring force towards the opposite direction, so you would have to change your direction again. That's why you constantly change your direction and you oscillate, not just move infinitely towards one direction. So if we draw a displacement time graph, it would look something like this. If you started from a position at 0, then you would move towards one direction, but once you reach a certain point, the restoring force that's applied to the opposite direction will be great enough to convert the direction of your movement and make your object move towards the opposite direction. However, same thing. Once you move toward the other direction and reach a certain point, then the restoring force towards the initial direction will be greater. And again, your object would convert its direction and move towards the opposite direction again. So this action, this motion will continue on and on and on. We call this motion as simple harmonic motion. Now, in simple harmonic motion, there are a lot of elements, a lot of variables that you have to know. First is displacement. Basically, and before we learn about displacement, it's important to know what equilibrium is. Equilibrium is a middle point. The points in the complete middle in the graph, these blue points, or if we come back to the spring example, it will be the complete middle over here. Equilibrium, as you can see, is the point where there is zero force involved. There's zero restoring force. Why? Well, if you move a little bit right from the equilibrium point, you can see how now you have a direction of movement. Thus, there will be an opposite direction restoring force applied to this object, which would head towards the equilibrium. Now, if you move to the left of the equilibrium, then again, you'll have the restoring force that points toward the opposite direction of your movement, which would again point towards the equilibrium. In other words, the restoring force always points towards the equilibrium, because what restoring force wants to do is it wants to make your object move and go back to your equilibrium position. So equilibrium position is sort of like the ideal middle position where there can't be a restoring force. I mean, think about it. Restoring force points towards the equilibrium position, but if you're already at the equilibrium position, you can't have any restoring force. That is why the definition of the equilibrium point would be the point where there is no restoring force, or the point where there's absolute zero net force. Or an easy way to understand it, it's the middle. It's the middle. If it's a spring, if it's a pendulum swinging, the equilibrium would be in the middle. So yeah, that's how it works. Now, displacement. Let's talk about displacement. Now that we know what equilibrium is, now we can actually talk about displacement. Displacement is basically the distance between the equilibrium position and the position you're at. So if we go back to this drawing, if the box is on the green position, then this position displacement would be the distance between the equilibrium position, so in this green line, and the position where you are actually at. So the distance between the two green lines would be the displacement of this object at this given time when the box is at the green position. So that is displacement. And of course, again, displacement has positive and negative value. So positive value normally would mean right of your box, and negative value would be left of your box. And that's why if you draw a displacement time graph, you can see how it moves towards positive direction first, and then move down to negative, move back to positive, and that would continue on and on and on. So that's displacement, the distance between your object and the equilibrium position. Now what we can know is that at equilibrium position, then of course displacement will be zero, because again, displacement is the distance between your object and the equilibrium position. But if your object is at the equilibrium position, then the distance between the two would be zero. That is why on the displacement time graph, you can see how equilibrium positions are on the point where the object is on the equilibrium. So the equilibrium position is on the point where displacement is equal to zero, because that is when the object lies on the middle on the equilibrium position. Now, then what is amplitude? Amplitude is the maximum value of the displacement. So in this case, in this graph we have over here, this green arrow, the length of this green arrow would be the amplitude, the maximum value of displacement. Basically, it's the distance between the equilibrium position and the position that's the farthest away from the equilibrium position. How far away can the spring actually extend to in this given simple harmonic motion? That would be the amplitude. Well, amplitude also appears in waves and stuff, and it literally means the same thing over here as well. It's the distance between the equilibrium position, the middle, and the right end or the left end. Either end doesn't matter. Which end it is doesn't matter. It's basically the distance between the middle and the end. Now, what is period? Well, period is the time it takes for one simple harmonic motion cycle to occur. Now, when we say one cycle, let's go back to this graph. I'll draw another graph since this one's kind of messy now. So if you have such graph, when you say one cycle of the simple harmonic motion, it's basically when one full series of actions in the simple harmonic motion takes place, right? And that would be, if you start from one position, you have to come back to the position, not only just come back to the position, but you should come back to the position at the same phase. And now phase is another thing we have to learn. And basically what phase is in a simple harmonic motion is phase is position plus the direction you're moving towards. So if we think about this spring example again, let's draw another set of spring. Now let's say this point is the equilibrium point, and you pull the spring towards yourself, and now the spring is moving in a simple harmonic motion. Now let's say the spring is positioned over here at the blue position. Now what you can notice is that there could be two different scenarios. Scenario one is when the box is on the blue position and it's moving towards right. It's still extending. The spring is still extending. The other possible option is that your object is on the blue position and it's moving toward left. It's now getting shorter and it's moving towards the equilibrium position. So even in the same position, the object in the simple harmonic motion can have two different directions of movement unless you're at the complete end of the simple harmonic motion. Because when you're at the complete end, you don't have a direction. You're always changing your direction. Thus, you're not moving anymore. You're changing your direction. You're not either going left or right. You're just on the spot, just turning around. However, apart from those two very specific situations, in the middle of the simple harmonic motion, always in every position, the object can be either moving towards moving towards farther away from the equilibrium position or moving towards getting closer to the equilibrium position. So there might be two possible cases. Thus, what phase is talking about is basically, it's not simply where your object is at, but it also talks about where your position is at plus where it's moving towards. So it's literally the phase. So if we come back to our graph, points 1 and points 2 are on the same position. However, they're moving on a different direction. In phase 1, you can see how the graph moves upward in the next moment, but in phase 2, you can see how the graph is moving downwards in the next moment. Thus, they're on the same position, but they're moving in the opposite direction. However, if we compare phase 1, point 1, and points 3, they're both on the same position. They're both on the equilibrium position because the displacement is 0, and you're both moving upward in the next moment. Thus, you're on the same position, plus you're moving towards the same direction, meaning that you're on the same phase. And again, period is the amount of time it takes for the object in the simple harmonic motion to move from one phase to the same phase, but in the next cycle. Thus, the period of a simple harmonic motion would be the time it takes for one cycle to occur and the object to come back to the initial phase. So basically, in easy words, cycle or period is the time it takes for the simple harmonic motion to go through one of this double hook shape motion. So I went through the basic elements of simple harmonic motion. I hope you understood all of them. And now let's talk about different types of simple harmonic motions present. Well, we have a spring, and that's literally what I've been talking about the whole time. So I'll just skip this one. Second is a pendulum. If you have a pendulum attached to the wall or the ceiling, and it's moving from left to right and right to left, and if that continues, then the movement of this pendulum would be a simple harmonic motion. Why? Well, unless it's in the equilibrium position, if the pendulum is on a different position, it would have a restoring force that tries to pull the pendulum back down to the equilibrium position. Thus, always there's a restoring force that applies onto the object to the opposite direction of the direction the ball is moving towards. Thus, it is a simple harmonic motion. And of course, you have the other two, block on water and LC circuit. Well, to talk about the block on water, basically it's something like this. If you have a tank, if you have water in the tank, and if you have a block, and if you press the block down, then the block will kind of sink, but then it's going to float back up. And then once it floats back up, it's going to sink again and float back up, sink again, float back up, and that motion will continue. So that would also be a simple harmonic motion. Same with LC circuit, but to be honest, block on water, LC circuit, and many other examples never appear in AP Physics 1 test. So it's just good to memorize the two things we have over here, the spring and the pendulum. Now that being said, I just realized that I missed one important thing, which is for the period, yes, you can find out the period of a given simple harmonic motion by looking at the graph and looking at how much time it takes for the graph to go through one cycle of this double hook shaped graph. However, if you're not given a graph, then you can calculate it by a formula 2 pi square root m over k. Now, K would stand for the constant. And if it's a spring simple harmonic motion, then K would be the elastic constant of the given spring. And M is the mass of the object attached to the spring. Now, if it's a pendulum, then you would have to use a different formula to calculate the period, which would be 2 pi square root L over G. Now, again, G is a constant. It's a gravitational constant, and L is the length of this pendulum. Now, what's important is that when it's a pendulum, the mass of the marble that's attached to the end of the pendulum does not matter in terms of period. The only thing that matters is the length of the pendulum and the gravitational constant, but gravitational constant it's a constant, so it won't change anyways. So that's a quick note. And then finally, let's talk about the graphs. Well, I've already talked about the xt graph or the displacement time graph. So from this graph, what you can know is that equilibrium position is when x is equal to 0. And this points, the highest points and the lowest points would indicate the points when the spring is either compressed the most or when the spring is extended the most and thus farthest away from the equilibrium position. Now, then, what would be the velocity at each given point? Now let's think about it. When your block is at the equilibrium position, would the velocity of your block be high or low? Well, it would be extremely high. How do you know that? You can know that in two reasons. First is graph analyzing. As you can see from the xt graph, the slope at the equilibrium position, or when x is equal to 0, is the greatest. And since the slope of displacement time graph is the velocity at the equilibrium positions would be the highest. However, there's also a different way to figure this out, which is doing some mind processing in terms of physics. Let's think about it. If you're at the complete middle, that means that you don't have any restoring force. If you're at the equilibrium position, the definition of equilibrium position is the point where there is no restoring force, since restoring force applies to the opposite direction of where you're moving at. If you don't have the restoring force, then of course your velocity would be the greatest, because always restoring force decelerates your force, your velocity, the velocity of the object. Thus, in the equilibrium position where there's no restoring force, of course, the velocity of the object would be the greatest. So for two different reasons, you can figure out that the points where the equilibrium position, where the displacement used to be 0, in fact, has the highest velocity. Now, what about this highest points? What about these green points? Well, what you can know about these green points is that the displacement is maximum. In other words, it's either your object is either compressing the spring to the maximum or extending the spring to the maximum. Now, what you can notice is that at these points, the velocity would be 0. Why? First reason, if you look at the graph, the slope is 0. Since the slope of the displacement time graph is the velocity, of course, the velocity at these maximum points, maximum displacement points, would be 0, like these. However, you can also reach to the same conclusion by doing some physics mind processing. If you think about it, when you're at the highest point or the lowest point on the graph, it means that you're either expanding the spring to the maximum or compressing the spring to the minimum. In those cases, is your spring moving at all? Not really. It's turning around. It's changing your direction. Think about it. You have a super fast car, but once the car reaches this position, the car turns around. Now, when the car is turning around, is there a velocity? No, the car would stop instantaneously and then again start moving towards the opposite direction. So this point would be the point where velocity is actually 0, because the velocity have to change from positive to negative, meaning that there should be a 0, a point where it's 0 between the two. Thus, this point where the object is actually turning, it's changing its direction, the velocity should be 0. So we can process it in, again, both physics way and in math way using the slope. Now, let's think about acceleration. But before we think about acceleration, it's important to remember that acceleration is in fact a result of force. If you see my second video about dynamics, you would know that force is literally what creates acceleration, and acceleration is what is created by the force, meaning that the acceleration and the force has the same direction. They're both vectors. So in order to find the magnitude and the direction of the acceleration, you just have to find the magnitude and the direction of force. And what force is present in simple harmonic motion? The restoring force. Now, that being said, let's look at this diagram again. So again, I'm going to use the spring object diagram. So this red part would be the equilibrium position, and these green boxes would indicate the minimum and maximum displacement points. Now, what you can notice is that when your box is at the green positions, it means that your green checkpoints, it means that the spring has extended to its maximum or compressed to its minimum. Thus, it's farthest away from the equilibrium position, which means that the restoring force should be the greatest. I mean, if we just think about the elastic force, the formula of it is F equals to Kx. K is a spring constant, so it doesn't change, and X is a displacement, meaning that the elastic force is greater when displacement is greater, and the displacement is the greatest at these two green checkpoints, which is literally the two ends of the simple harmonic motion. Thus, at the end of the simple harmonic motions, you should have the maximum force, meaning that maximum acceleration. So you have the green points in this graph over here. Now, what if your box is at the equilibrium position? Well, again, equilibrium position literally means the point where there is no restoring force. No force means no acceleration made. Thus, in the equilibrium positions, you should have 0 acceleration made. This is how you analyze xt, vt, and at graph. Please do not blindly memorize the graphs, but try to understand and actually draw the graphs. How this work? Why does the graph work this way? Oh, it works because of the slope relationship, because in math-wise, oh, it works because of because force is related to acceleration. Please try to understand those concepts. Once you understand the concepts, everything else will come so easily. Now, that's it for the 6th unit. Thank you for listening to my class as usual, and please don't forget to have a great day. Bye-bye.